Hello everyone, welcome to this tutorial about QMM calculations. In particular, this tutorial is the computer exercise we were doing also in the lecture, but it's very likely that we will not have the time to finish the exercise. So this is why I'm recording this video, because then you can finish at home the computer exercises following the steps I will describe in this video. Okay. Okay, so let me share my screen. 1 second. Okay. Okay, so this is the computer exercise we are doing. So we are simulating the thymine-thymine dimerization by applying quantum mechanics, molecular dynamics in combination with the umbrella sampling technique. So as you know, this lecture is about QMM, so you should study molecular dynamics in other course probably, and also enhanced sampling techniques, including umbrella sampling. But anyway, I will say here a few words in order to understand better the computer exercise, okay? So this is the reaction we want to investigate. Here we have two thymine molecules, which are consecutive in a DNA strand. And usually, when the DNA absorbs ultraviolet light, these two thymines can dimerize, giving rise to this reaction. Okay, so in particular, these two carbons reacts with these two carbons in a Diels-Alder reaction, and then we form here a four-member ring. Okay, so this reaction, as I said, happens usually after excitation with light. So it happens in the first electronically excited state, but for the sake of simplicity, in this computer exercise, we are going to simulate the reaction in the ground state because it's much easier and is computationally cheaper, right? Okay, you will see at the end of the computer exercise that the energy barrier for this reaction to happen in the ground state is very, very large. So it will never happen in reality. But we are going to apply an enhanced sampling technique, which is called umbrella sampling, in order to force the reaction to happen. Okay. Okay, so let's go to the computer. So let's go to the Chineca server. So I have it here already open. So in this computer exercise, we have to go, as you know, to the work folder, which is the folder you were working for the last weeks in the intensive course. And here we have several folders from different lecturers. And in particular, the folder we are going to use is the QMM one. And inside QMM, we go to the TT folder, which is the thymine-thymine folder. Okay. Okay, so here you will see 6 different folders because in this computer exercise, we need to perform 6 different tasks in order to simulate the reaction. Okay. So in the first step, we need to do the setup of the system. So we are going to go to the WHAM setup folder. And here you will find 2 different files. So the first file, the nuc.nav, is a program. NAV stands for Nucleic Acid Builder, which is a language, a programming language which is implemented in the AMBER software. And this programming language is very useful because it allows us to create DNA strands. Okay. So for example, here you can go to the AMBER 20 user manual for more details, but here we are going to see the basic things, let's say. So here we want to build a double-strand DNA. This is why here we have AB. Okay, that means we want to create a double-strand DNA, and this double strand, in one of the strands, we are going to have 10 thymine nucleotides, and automatically, of course, the program knows that in the other strand we should have 10 adenine nucleotides, right? Okay, so this will be our DNA strand because later we are going to take the two thymines in the middle of the strand, sorry, the thymine number 5 and 6. And these two thymines will be the fragments which will react with each other. And this will be the two thymines that we need to describe at quantum mechanical level, okay? Okay, so we create the DNA strand and then we save the strand in Pdb format. Okay, Pdb stands for Protein Data Bank. Probably many of you knows already about this. This is a coordinate format, and probably many of you knows about it. But in a minute, I'm going to open the file, and you will see how is the format of this coordinates file. Okay, so the first thing we need to do is to compile the program. So we need to compile this nuke.nap. So let's do it. But by the way, before compiling it, sorry, I forgot to say, we need to load the Amber program. Okay, and in order to load Amber, we need to type module load live sc Amber. I think. No, sorry. 1 second. No, I have here anyway the. Okay. Module load profile live sc. Okay. And now we need to load Amber, and we need to type module load auto load Amber. Okay, perfect. So in order to be sure Amber is already loaded and it works properly, for example, we can type which Sander, because Sander is a program inside Amber, and see if we find it in the system. And as you can see here, Sander is located here in this pathway, so everything is fine. So Amber is loaded properly. Okay, so now, as I said, what we need to do is to compile the program. So let's compile nuke.nap in this way. It will take a few seconds. Okay, so after compilation, as you can see here, we have generated here an executable program, and this is the program. This is the file we need to execute now. Okay, if we execute nuke, what we are going to do is to generate here this DNA0.pdb. Okay, so this is the file where now we have the coordinates of our DNA strand. Remember, in our DNA strand, one of the strands is formed by 10 thymines, and the other strand is formed by 10 adenine nucleotides. Okay, we are going to visualize this in a minute, but for the moment, let's open it with VI. Okay, just to see the format. So this is a Pdb file. I will not go through the entire file, but it's not difficult to understand. So here we have the X, Y, and zeta of the atoms. So this is the atom number 1, which is a hydrogen. In the Amber force field, this hydrogen in the DNA strand is called HO5'. Okay, this is just the Amber nomenclature. And this atom belongs to a thymine residue, to the first thymine of the DNA. This means, this one means, this is the residue number 1. Okay. Then we have the second atom for this first thymine residue, the third atom, and so on and so forth. If we scroll down, at some point now we have here the residue number 2, which is also thymine. And okay, let's scroll down. Remember, we have 10 thymine residues in the strand. So this is the last one, should be the last one. Okay. Okay, so, and here, this is the last atom of the 10th thymine residue in the first strand. Then we have here a termination keyword, and then we start the second strand. And now in the second strand, as you know, we have 10 adenine residues. Okay, so this is the residue number 11, which is adenine. Okay, and as I said, X, Y, and zeta coordinates. Okay, so this is the important thing of this PDB file. Okay, if you like, we can visualize it. In order to visualize the trajectories and the molecules of this computer exercise, we are going to use a visualization program which is called Visual Molecular Dynamics that probably you have already used in other lectures, especially in the molecular dynamics lectures. Okay, if we want to visualize in the Cineca computer trajectories or whatever thing we want to visualize, as probably somebody already explained you, we need to open a RSM session. Okay, so let's open the the RCM session in the Cineca server. Okay, so okay, so now we need to create a session here, plus, we click here in this plus, we are going to connect through SSH, so everything is fine, the defaults are okay, so we click OK, and we wait a bit. Okay, so let's wait for the terminal. Okay, here we have our terminal. So now, so we are connected exactly in the same computer as we are in the other terminal, so we need to go to work, $work, and then QMN, TT, and if you remember, we are here in the folder 1 setup. Okay, so we want to visualize this file, dna0.pdb. So in order to visualize files with visual molecular dynamics, we need to load the program. And in order to load the program, we have here the keywords because I never remember them. Wait, sorry. So first, we load the ChemFis module. Then we load VMD itself. And finally, we need to call VMD. Okay, sorry. Okay, so we need to load the module ChemFis, VMD, and then we execute VMD in this way. Okay, so let's do it. Okay, so here we have the main window of visual molecular dynamics. So here we have all the options we can use on the left panel, and on the right panel we are going to visualize our molecules and our trajectories. Okay, so in order to load the PDB file, let's click in File, New Molecule. Now we have this new menu, and in this menu we click Browse. And here we have the PDB file, dna0.pdb. So double click. And now, as you see here, automatically VND recognize we are loading a PDB. This is not always the case. Sometimes the automatic recognition doesn't work, but for PDB files it's fine. So we click load. Okay. So here we have our molecule. If you want to rotate the system, you can just click on the left button of the mouse and then move the mouse. As you can see here, the screen is a bit cut. This is, I think, a problem with Cineca. So let's translate the molecule. To translate the molecule, press the letter T, okay, in the keyboard, T, and then you can press the left button of the mouse and move the strand up and down, okay? If you want to make zoom in and zoom out, you can click S, okay? S stands for scale, and then you click the left button of the mouse, and again, you can do zoom if you move to the right, and you can unzoom if you move the mouse to the left, okay? And if you want to come back to the rotation mode, you click again R in the keyboard, and then you can move the mouse, clicking the left button of the mouse, okay? Okay, so this is our DNA strand. Everything looks fine. So we have one of the strands is composed by 10 thymines, and the other one is composed by 10 adenine residues, okay? So everything looks good. So let's come back to our terminal. Okay. So in order to run dynamics with Amber, we need to create one file with the coordinates. We already have here one file with the coordinates, but this DNA for the moment is in vacuum. If we want to simulate a realistic thing, we need to solvate the molecule, okay? And also, I don't know if you know, but a DNA strand, so the nucleotides are connected by phosphate groups, and these phosphate groups are negatively charged, okay? So this DNA strand has a lot of negative charges, okay? So in order to run molecular dynamics with periodic boundary conditions, probably you have studied the periodic boundary conditions in other lecture. So the charge of the cell, the charge of the system has to be 0. Otherwise, the equal summation doesn't converge properly, okay? Probably you have studied this in your molecular dynamics lectures. If this is not the case, you can go also to our YouTube channel, and we have there a couple of lectures where we talk about periodic boundary conditions and the equal summation, okay? But anyway, for this tutorial, we don't need to explain it. The important thing is we need to have a neutral system, so we need to add some sodium ions to neutralize the negative charges of the phosphates, and then we are going to solvate the system, okay? And we are going to do this with a utility in Amber, which is called tlib, okay? tlib. Later, we are going to execute tlib. tlib needs an input file saying what you want to do, okay? This is the input file for tlib. So here at the beginning, we are loading all the relevant force fields. Indeed, for this computer exercise, we need only to load the DNA force field and also the water force fields. This force field already includes the parameters for the ions also, okay? Indeed, we don't need the other lines, but I always load all the relevant force fields because it doesn't hurt. So this is the force field for proteins, this is for membranes, and this is for organic molecules. So I usually load all the force fields, and then I use whatever I need, okay? So here in tlib, what we do first is we read the Pdb file. Okay, this is the Pdb file we have created a few minutes ago. Now, we are creating here this variable, mol, where mol is our DNA strand. So now we add ions to this system, mol. So we are adding sodium ions until the charge is 0. Okay, that's the meaning of this. Then we solvate the system. We are going to use the TIP3P model for water that probably you have studied also in your molecular dynamics lectures. And we are going to use a truncated or octahedral box. Okay, this octahedral shape is very efficient when we want to apply periodic boundary conditions. Okay, so it's, let's say, the shape of the box which allows you to, let's say, to contain the less number of molecules possible. So the simulation is very efficient. Okay, and this thing means the separation between any solute, any atom of the solute and the end of the box is at least 10 angstroms. Okay, so we are adding, let's say, a 10 angstrom radius buffer. Okay. Okay, so we neutralize the system, we solvate the system, and now we are ready to save the two files which are needed for the dynamics. So here we are going to save this file which contains the parameters, the force field parameters of our system. So the DNA strand plus water plus the ions. And here, by the way, this PRM top stands for parameters and topology. And then we also save this other file, which is called a restart file, which contains basically the coordinates of the system, okay, but in a different format than the Pdb file, okay. We can open it in a minute. And then just in case, this is not needed, but just in case, we also save the Pdb, okay. And then we exit the program. Okay, so let's execute it. I will clear the screen. Okay, we can execute it as tlib -f tlib.in. When we write here -f, means that after the f, after this, we are going to provide an input file here. Okay, because we can also run tlib in an iterative way without providing an input file. Okay. Okay, so let's execute it. Okay, everything finished correct. We don't have errors, we don't have warnings, so everything is fine. And here, now we have created the parameter file. We can open it if you want, but we will not explain it in detail because it's a very complex file. So here, basically, you have, as I said, I will not explain it in detail, but here we have the parameters of our force field. Okay, all these numbers we have here. For example, okay, let's look for force. So here we have the force constant of the bonds. These are the values of the force constants we have in our system. For example, we have also here the angle force constants. We have the Lennard-Jones parameters, the charges, the dihedral parameters, and so on. Okay. If you Google topology file for Amber, you will find an explanation of all these sections, but for the sake of simplicity here, we don't need to know everything, all the details, okay? Okay, so this is one of the files. The other file we have generated is the restart file. If we open it, it's a simple file where we have here the number of atoms. So we have almost 13,000 atoms in our system. So this is why we want to run first the classical molecular dynamics, and then we are going to treat only a small region of the system with quantum mechanics, okay? Of course, we cannot treat the full system with quantum mechanics, okay? So here we have x, y, and zeta coordinates for the first atom, x, y, and zeta coordinates for the second atom, third atom, fourth atom, and so on and so forth, okay? And if you go to the last line, here you will find the dimensions of the box, okay? So you need 3 distances and 3 angles in order to describe a truncated octahedron, okay? Okay, so if you would like, let's visualize these 2 files. So we can visualize directly the Pdb. In the Pdb, by the way, so we have again our DNA strand, but at some point we also have, so you can see here, the sodium ions and the water molecules, okay? So we can visualize the Pdb as we did before, but we can also visualize the system loading these 2 files in VND. Okay, we can load the parameter file and then the restart file to visualize the system. So let's do it. So we need to go again to this graphical session we have open here. So in order to delete this molecule we have loaded before, this is the DNA in the gas phase from the previous step. So we can click the right button of the mouse and then we click here, delete molecule. Okay. And now we click browse, and then now we can load the parameter file, dna.prmtop. Okay. Now Amber VND recognize automatically this is a Amber parameter file, so it's fine. We load it. Here, for the moment, nothing appears, but as you can see here in the VND main window, we have already the number of atoms, right? Okay, so we click again, browse, And now we are going to choose the restart file, RST. Okay, if you look here, now VND doesn't recognize the file. So we need to look for the file type, and this is a Amber7 restart file. Okay, we load it. Okay, so here is the file. I will again translate the system. Remember, we press the T letter and then the left button of the mouse, and then we move the mouse, okay, in order to center this. And then we can come back to the rotational mode, clicking R and moving the mouse again, okay. In order to zoom in and out, you can also scroll with the mouse, okay. If you don't have the wheel in the mouse, you can also remember clicking the letter S and then move the mouse to the right and to the left. Okay. Okay, so this is our simulation box. This is the famous truncated octahedral. Okay. And here, if you want to represent, for example, only the DNA, we can go to graphics representations. And here we have by default all, right? This is why we are seeing the full system, but we can write here nucleic, for example. And if you write nucleic, you only see the DNA strand, okay? And for example, there is a very nice VND tutorial in the internet, but for example, if you want to visualize the residues number 1, 2, and 3, for example, you just write res ID 1, 2, and 3, okay? And these are the first 3 nucleotides, okay? Okay, let's come back to all. Okay, what happens? Sorry. Okay. Okay, good. But by the way, if you just a nice representation for DNA, here in the drawing method, the default is lines because it's the more efficient one. Otherwise, BND can, take a lot of time loading the molecule. But then you can change the visualization mode. For example, you can choose here a new cartoon, for example, and you have this nice representation. Okay. Okay, good. So we come back to the other terminal. Okay, so this was the first step. In the first step, we have created the parameter files that contains the parameters of the force field of our system, and then the restart file, which contains the coordinates. Okay. Okay, now let's go to the folder 2 classical ND. So here in this folder, in 2 classical ND, we have 3 different input files called min.in, hit.in, and md.in. So here, in the next step, we are going to perform classical molecular dynamics for DNA strands. So in this step, everything will be still described by the force field. Okay, so there is no QMMN yet. Everything will be classical. Okay, we need to perform 3 steps. And this is usually the case when we run classical molecular dynamics for any system, okay? First, we need to minimize the system. We need to reach a geometry which is low in energy. I will explain you in a minute why. Then, once we are in a minimum, we need to heat the system to the desired temperature. And the heating has to be smooth because sometimes we can destroy the system. And finally, we need to perform an equilibration, okay? And this equilibration, I will tell you in a minute. Usually, we run the equilibration with the volume, allow it to change. So we don't run at constant volume, we run only at constant pressure, because one thing we want to equilibrate is the density of the system, okay? And usually, the way to equilibrate the density of the system is allow the volume to change, okay? So let's come back to these slides, 1 second. Okay, so let's say this is the potential energy surface of our system, okay? So as you know, we are going to solve the Hamilton equations, right? These 2 equations allows us to compute the variation of the coordinates with the time and the variation of the momenta with time. Okay, so solving these equations by, for example, using the velocity-Verlet algorithm, we can compute the evolution of coordinates and momenta with time. Okay, in our channel, in our YouTube channel, we also have some lectures about classical molecular dynamics. Okay, in case you want to watch them. Okay, so let's say this is the potential energy surface. Now we have created an initial structure with amber, right, with tillit. And let's say the initial structure, for example, is here. For example, these are the coordinates of the initial structure, so the energy is this energy here, okay? And now let's assume that the thermal energy, so the energy available in the system because of the temperature, is represented by this line. What happens if we have this situation? First, what happens if the thermal energy is this one? So this means that during the simulation, the system should populate only this region of the potential energy surface, which is thermally accessible. So it's very difficult to populate this region here. Only if we wait for a lot of time, maybe seconds, minutes, or even hours, maybe the system can reach this region of the potential energy surface, okay? But in a realistic situation, in a realistic simulation, the system should be here in this region of the potential energy surface, in the low energy region, which is below the thermal energy. But the problem is TLIP is not, let's say, intelligent. Maybe the initial structure is not so good and the energy is this one. If we start the simulation from here, we have a lot of energy and the system can reach this region of the potential energy surface, which should not be populated, okay? This is why before running dynamics, we always have to minimize the energy of the system, okay? So we need to minimize the system to the closest local minimum, maybe here. Now we have a reasonable amount of energy. So from here, we can start our simulation, okay? So once we are in the minimum, as you probably know, the temperature classically, not classically, I mean, the temperature is 0. So the next step is to heat the system, okay? So we need to increase the temperature or we need to increase the kinetic energy of the atoms slowly until reaching the desired temperature, okay? And once we have the desired temperature, then we run the classical molecular dynamics, we solve Hamilton equations at the desired temperature, and then we are able to explore all this region, which is thermally accessible, okay? So these are usually the 3 steps in molecular dynamics: minimization, heating, and production, or equilibration, okay? Equilibration and production, let's say they are the same step. They are the last step of the simulation, because usually we run a very long production simulation, and from this simulation, we take out, so we delete the first steps of the simulation because the system is still equilibrating, okay? Okay, so let's come back to the terminal. So we have here these 3 files: minimization, heating, and MD. So let's execute the 3 steps at once. First, let's execute the steps, and then I will explain a bit the 3 files, okay, the 3 input files. So in order to submit this calculation, sbatch and then run.sh. Okay, here in run.sh, okay, so here we are loading Amber. Okay, these are the, you know, the computational time, the number of tasks, the number of nodes, and so on. And here is where we are calling pmemd. So pmemd is the program in Amber which runs the dynamics, okay? We are using the parallel version. And here we have the input file that we are going to see in a minute, the output file, in this output file, we're going to print the information at each step of the dynamics, like the energy, the pressure, the volume. So we print the evolution of the properties of the system. Here we have the parameters of our system, the force field that we have created with tlib. This is also the file with the coordinates that we have created with tlib. And now this is where we are going to print the minimized geometry. Okay, after the minimization, this will be our minimized geometry. Okay, and now we need here a reference geometry, and I will explain you why in a minute. Okay, this is a reference geometry that we need because during the minimization we are going to apply some restraints. Okay, but I explain this in a minute. For the moment, the important thing is our minimized structure is this one. This minimized structure will be the starting point for the heating. So in the next line, in the heating, we have here the input file for the heating that we open in a minute. Okay, this will be the output file where again we are going to print the time evolution of some properties, the parameters, and now the initial coordinates are the minimized coordinates that we have obtained in the previous simulation here. Okay, and now the final coordinates after the heating will be saved here in heat.rst. Again, we need a reference coordinates because we are going to apply some restraints. Okay, later I explain the restraints. And this file is the file where we print the coordinates of our system every n steps. So in other words, here we are going to have the time evolution of the coordinates, and we can open later with VND this file, and we are going to visualize the nice movie of the heating of our system. Okay, so as I said, the last coordinates after the heating will be saved here. So these coordinates will be the initial coordinates for the production dynamics. So for the next step, in the next step, we run the production. This is the input file. Again, the output file with the time evolution of the properties, parameters. And now these are the initial coordinates, okay? The final ones from the heating. And then you know already what this is. This will be the final coordinates after the production simulation. And finally, here we are going to have our nice movie to be visualized with VND. Okay, so this is what the script does. So now we are going to have a look at these input files in order to understand better what are we doing. Okay. So let me check if something was wrong, because I think that the simulation crashes. Okay. Of course it crashes. Let me delete the output files. Okay. Before running anything, of course, what we need to do is we need to copy from the previous folder, from the setup. We need to copy the parameters and the RST. Okay. Of course, we need these two files to start the dynamics, right? So now let's submit it again. Okay. Hopefully now it will work. Okay. Now, if you open the minimization input file, I will not go through all the keywords because they are explained in the PDF that I provide. But here in the minimization, basically what we want to do is to minimize the system for 1000 steps. We are going to use periodic boundary conditions at constant volume. So we are running the minimization in the MVT ensemble. And this is the cutoff for the Lennard-Jones interaction and also for the real space equal summation that you probably studied in other lecture. Okay, so this is the minimization. After the minimization, we need to hit the system. And in order to hit the system, so I explain only the basic keywords. Again, periodic boundary conditions at constant volume and temperature, the cutoff. Okay, we applied here the shake approximation. In the shake approximation, we assume that the bonds containing hydrogen atoms are not relevant for the dynamics, so we can freeze these bonds containing hydrogen, and because of this, then we can use a larger time step in the dynamics, okay? So, and this will accelerate the dynamics. For example, if you use the shake approximation, then the time step could be set to 2 femtoseconds. Otherwise, if you don't freeze the bonds containing hydrogen atoms, you need to use a time step of 1 femtosecond or 0.5 femtoseconds, okay? Because the frequency of vibration of the bonds containing hydrogen is very, very high. So we need a very small time step in order to reproduce such a vibration, okay? Okay, so this is our initial temperature, the final one. This is the thermostat we are using, the Langevin thermostat, and this is a parameter of the thermostat, okay? You can go to the Amber manual if you are interested in these parameters, okay? But for this lecture, we don't care too much. So we are going to run the heating for 5,000 steps. This is a very short simulation because it's 5,000 steps multiplied by 2 femtoseconds, which means we are running 10 picoseconds. It's a very short simulation. A real one, maybe, I don't know, in a real one, we should heat the system for half nanosecond at least. But here, for the purposes of this tutorial, it is enough, okay? Okay, these are printing options that you can read in the manual. And now, this keyword means we are going to apply a special restraint. And the special restraint will be a smooth temperature increase. And here we have, in this section, these temperature restraints. This means that from the step number 0 to the step 4,000, remember we are running 5,000 steps. So until the 4,000 steps, we are increasing the temperature from 0 to 300 Kelvin. And then in the last 1,000 steps, we keep the temperature constant, okay? That's the meaning of this. And now, remember that when we submit the heating, we have here this reference, okay? And I told you, indeed, we also have here the reference in the minimization, but indeed, it's not needed, okay? So here, sorry, here is not needed, okay? But in the heating is needed. And this is because of the following. So here in the input file of the heating, we are telling Amber that we're going to apply positional restraints, okay? And in particular, we are going to restrain the motion of the first 20 residues. And the first 20 residues are the DNA residues, okay? Is the DNA strand, okay? And in particular, we are going to apply a force constant of 10 kilocalories per mole square angstrom. And that means that in our system, we are going to have our atoms, okay? The initial position of the atoms will be the reference geometry. So this geometry we are providing here, okay? And then let's say the evolution of the atoms with time will be somehow attached by a harmonic potential to the atoms of this reference structure. And the force constant of this harmonic spring is 10, okay? So that means the DNA strand, these 20 residues, will not move too much from the initial position, from the reference geometry, okay? Because we have this harmonic potential, which is restraining the motion, okay? Okay, good. And finally, let me see, by the way, if the simulation is running well. Yes, now it looks okay. So finally, for the production, so everything is more or less similar as in the heating, but now one thing we are doing different is we are restarting the simulation from the heating. What means restart the simulation from the heating? So we are going to read not only the coordinates from the heating step, but also the velocities and the box information. The velocities are important to be read from the heating step because if we read the velocities, automatically we start at 300 Kelvin, right? Because the last step in the heating, the temperature of the last step is 300 Kelvin, okay? So this is the reason why we need to read the velocities. We apply periodic boundary conditions, but now in the MPT ensemble, that means the volume now is allowed to change. And you will see in a minute that this is necessary because the density has to be equilibrated. Okay, usually the density is very low, so we have to increase the density by decreasing the volume. Okay. Okay, so these are the barostat options in order to control the pressure. We are using a Berensen barostat. You can go to the Amber manual to see the details. Again, the cutoff for the intermolecular interactions, the shake option in order to freeze the hydrogen atoms, okay? Now, the temperature, 300 Kelvin. Again, the thermostat. Now we are running the simulation for 10,000 steps, which means 2 femtoseconds multiplied by 10,000 is 20 picoseconds. Again, it's a very short simulation. If, let's say, if you want to publish a paper with a DNA strand simulation, I mean, it depends on the property you want to investigate, but at least we have to run 100 nanoseconds and probably much more, okay? Okay, and again, we have here some printing options. Okay, so that's it. So the simulation has finished. So let's open, for example, the dot file, the minimization.out file. Here, okay, let's go to the important part. So here we are printing the information every 50 steps. Remember that we are minimizing the system for 1000 steps. And here we are printing the total energy, the bond energy, the angle energy, the dihedral, and so on, okay? And since we are minimizing the system, the energy has to decrease with the number of steps, right? Because we are going to a local minimum. So this number is smaller than this one, right? It's more negative, right? Okay, so the last step is step 1000. So we are close probably to a local minimum, so we can stop the simulation, okay? Now let's open the heating, okay? Heating.out, and let's scroll down. Okay, so here we are. So for example, in the step number 50, the temperature is 9 Kelvin, okay? Now, for example, in the step number 200, the temperature is 20 Kelvin. So we are increasing the temperature, okay? Since we are increasing the temperature, the energy, of course, has to increase also, right? Okay, so let's go, for example, to the step, I don't know, here. 2100, this is the step, and the temperature is 123. Okay, so as you can see, we increase the temperature. So for example, I don't know, in the step 4250, we are already close to 300, okay? Okay. And in the last step, 5000, okay, it's still not 300, but we are close, okay? To be completely correct, probably we could run, I don't know, another additional 5000 steps in order to reach the temperature of 300 Kelvin, okay? If you want, you can do that, but it's not needed, okay? Because this system is very simple, okay? Okay, and finally, the production. Remember that the production was run at in the MPT ensemble, so at constant pressure, but the volume is allowed to change. And here you will see the reason. One moment. So this is the step number 100. The temperature is close to 300 Kelvin. And as you can see here, the density is only 0.87. Since we have a DNA strand in water, the density should be close to 1 gram per cubic centimeter, right? So the density is a bit small. So what we have to do is we have to decrease the volume. So this is the volume in cubic angstrom. And then after decreasing the volume, the density will increase. Okay, so if you want, we can check it. So for example, here in the step 2600, the density is already 0.96 because the volume has decreased. Okay. Okay. So if you go to the end of the file, okay, let's go to the last step. Okay. Here we are. No, this is still the average. Sorry. Okay, here. This is the last step. Sorry, 10,000, and the density is 1.02. So now is fine. So the density has been equilibrated. Okay. Okay. So if you remember, I will open again the run.sh script. I told you that, for example, in the heating or in the production, so here we have this file, which is called ndcrd, which are, I don't know, molecular dynamics coordinates, probably. And here we are saving the coordinates every n steps. Okay. If you are interested, by the way, the variable which controls the printing of the coordinates is this one. Okay. So here, so we are running 10,000 steps, and we are printing the coordinates every 100 steps. So that means we are printing 100 steps, right? So these 100 steps are saved here. Okay. So now we can visualize this trajectory with visual molecular dynamics. Okay. So in order to do that, we need to go again to the other terminal, where we have the graphics activated. Okay, I will close VND here because we need to change the folder. Remember, here we were in the folder 1. Now we need to go to the folder number 2. And we need to execute VND again. Okay, so file, new molecule, browse. The first thing we need to do is to load the parameters. Remember, automatically VND recognizes the file type, load. Here we have the number of atoms, so everything is fine. Browse again, and now we are going to load this one, ndmm.mdcrd. Okay, okay. Don't click load because here the program recognizes the file as a Amber coordinates file, but this is not correct. We need to use Amber coordinates with periodic box. Okay. Okay, so now we are loading 100 frames as we said, and here I'm going to translate the simulation. Okay, so if you click here in play, you will see the motion of the system. Okay, I will slow down it just to see something. Okay, so here in this option speed, you can slow down or accelerate the movie. Okay. Okay, so this is our simulation. If you like, if you want to play around, I don't know, for example, I'm going to create a representation. So now we have two representations. So in the first one, we can just represent the nucleic acid strand. We are going to choose, for example, Van der Waals representation. Okay, and now I will click twice here. If you click twice, the other representation disappears. So now we can see only the DNA. This is the DNA strand. Okay, and if you click twice again, you will see everything. Okay, I will now only put here water just to see the water molecules. Okay, so in the second representation, we only have water. In the first one, we only have the DNA. Okay. If sometimes if you see there is a kind of shadow over the image, in order to see better the movie, you can here go to display and deactivate this depth queuing. Okay. which is now everything is like more is brighter, right? Okay. Okay, good. So this is our movie. If we want to play around here also in the representations in periodic, you can also see how the periodic boundary condition works. For example, we can replicate the system in the x direction. So of course, here we are only replicating the water, but we can also, okay, let's replicate also the DNA. Okay, here it is. So this is our system replicated. So these are the periodic boundary conditions. We can also replicate the system in the white direction. Also the waters. Okay. And also the zeta one, for example. Okay, maybe it will be too much for my computer, but let's try it. Okay. What happened here? Okay, zeta. Okay, so of course I only replicated once, but you can here also click in twice, but maybe it's too much for the computer. Okay, so I will remove the zeta replication because I wanted to show you something. So here, as you see, we have some holes between cells. This is because our simulation was too short. But if you run the simulation for longer, maybe for 1 nanosecond or something like that, or maybe a bit less, you will see that the water molecules will occupy these holes and everything will be a continuum, let's say, system, which is as it should be, okay? But we have these holes still here because our simulation was too short, okay? Okay, so this is the classical MD simulation. Let's come back to the other terminal. So we have completed the step number 2, okay? So now let's go to the next step. In the next step, we are going to do again a molecular dynamics simulation, just the production part, the last step, but not with the force field, but with QMN, okay? With QMN. So let's come back to the slides. Remember, our goal is to simulate the reaction between two thymine molecules, okay? So, of course, as you know, with a harmonic potential as the amber force field, it's not possible to simulate a reaction, right? We cannot break or form bonds. So we need to use a reactive force field, or we can use also quantum mechanics, which will be our case, okay? So these two thymine molecules will be described quantum mechanically, okay? And these are the atom indices of the thymine fragments, okay? So now we need to tell Amber that these atoms will be described quantum mechanically, okay? So, by the way, if we come back to the VND representation here, okay, let me come back to just one cell. Okay, so I'm going to one second. Okay, self here. Okay, so I'm going to choose now not VND, but not van der Waals, sorry, but I don't know, lines, because I wanted to show you here the QM region. Okay, so the QM region we said is from the atom 139 to 152, 139, 52. So serial 139 to 152. And now the others are, one second, 171, 184. 171, 184. Wait, sorry, or serial. Okay, this keyword serial, you can select with this keyword. You can select the atoms by their index. Okay, so okay, So I'm going to represent the quantum mechanical region, for example, with licorice. And now I zoom here and you can see, okay, this will be our quantum mechanical region. Okay. Okay, good. So let's come back to the other terminal. Now, one second, which looks like it's not working. Okay, let me close VND. Maybe it's too much for my computer. Okay. No, it's not working, but doesn't matter. I will open a new terminal. One second. Okay, so okay, good. So let's go again. Can work, QMN, DT, and now we are in the folder number 3. Okay, so we have here the input file for the QMN molecular dynamics simulation. The first part is exactly the same as the classical simulation. Okay, so in this occasion we are going to run only 200 steps because we are treating part of the system with quantum mechanics, so the simulation will be more computational expensive. So this is just for the tutorial. 200 steps is okay. And now the new thing starts here. So here with this keyword, we are telling Amber we want to run QMN, not only the full force field calculation. And then we have here a section with the QMN details. Okay. So here we have the atoms which are included in the QM region, the charge of the QM region, the level of theory. We are going to use PM6 because otherwise the simulation will be very expensive. So this is a semi-empirical method that, as you have studied probably, in semi-empirical methods, we simplify, we represent some of the 2 electron and 1 electron integrals by empirical parameters. Okay, so the calculation is much computationally feasible. Okay, so the cutoff here, that means we are using the electrostatic embedding. Amber only allows for classical embedding and electrostatic embedding, so it doesn't have it has polarizable embedding, but not with all the force fields, only for a few ones. Okay, we are using the link atom approach. So in particular, we are adding a hydrogen atom. This is the separation between the hydrogen atom and the QN atom we are capping. And as we explained in the lecture, remember, we need to distribute the charge of the MM atom, which is linked to the QM atom, to the first QM atom, because otherwise we are going to have overpolarization. Okay, so we are distributing the charge of the MM atom linked to the QM region to the closest MM atoms. Okay. Okay, so this is the input file. In order to run the simulation, we are going to use this script. Here, by the way, now we are using Sander, not PMMD, because PMMD doesn't allow QMN calculations. So now we have to use another program in Amber, which is called Sander. Okay, with Sander, you can use QMN. Okay, input file, output file as before, where we are going to print the volume, the density, the energies, and so on, parameters. Now, the initial geometry will be, by the way, here we need to change the name because I think I call it before. One second. Okay, I think we call it before NDMN. So now the initial geometry will be the last geometry from the classical ND simulation. And the last geometry from this simulation will be saved here. Okay, and again, we have the movie. Okay, so what we need to do is first we need to copy the parameters and the last geometry from the classical simulation. Okay, and then we run the simulation. Okay. So the simulation is running. Remember, now we are treating the two thymines at quantum mechanical level. Okay. Okay. While this is running, okay, it's still pending, but it will start running soon, hopefully. So let's go to the next folder, which is the for one window QMN-MD, which is a bit weird, but I will explain you in a minute the meaning of this. Okay. So remember, we want to study this reaction. So here, these two carbons of one thymine will react with these two carbons of the neighboring thymine, and then we are going to form here a four-member ring, a cyclobutane, right? Okay, this reaction, as I said, in the ground state is very slow, right? Because the energy barrier is very high. I told you at the beginning that this reaction only occurs after excitation with light in the first excited state. But still, we can simulate the reaction in the ground state if we force the system to jump the barrier. And we are going to do this with umbrella sampling. Okay? In umbrella sampling, we have this situation. We have, as I said, a large energy barrier which has to be overcome. Remember, if we start the simulation here, the system will stay here forever because it will never jump the barrier. I mean, not never, but it will take a lot of time. For example, if your energy barrier is 20 kilocalories per mole, maybe this reaction is taking place in the millisecond time scale or microsecond time scale. And this is almost impossible to simulate nowadays with, let's say, a standard computer, okay? So we need to accelerate the dynamics in some way. And umbrella sampling is a good option when we know the reaction coordinate. And in this case, we know the reaction coordinate because we know which atoms are involved in the reaction, which are these four carbon atoms, 140, 142, 172, and 174. So we are going to define the center of mass between these two atoms and also the center of mass between these other two atoms. And then the distance between the two centers of mass will be the reaction coordinate, okay? And this reaction coordinate will go from, I don't know, for example, 4.5 angstroms to 1.3 angstroms, for example, okay? So this will be our reaction coordinate. Okay, so we have our reaction coordinate. In umbrella sampling, just a few words because you have studied probably umbrella sampling in other lecture. And anyway, if you are interested in our YouTube channel, we also have a lecture about umbrella sampling. But the first thing is we divide the reaction coordinate in several windows, okay? And then we apply, for example, in the first window, we apply a bias potential, which is a harmonic potential. So in order to keep the system trapped here in the first window, okay? So we run molecular dynamics with this bias potential, and then the system is here sampling this first window. When the simulation finishes, we increase the value, we increase the equilibrium value of the bias potential, and then we move the harmonic potential to the next window. And then we run a new molecular dynamic simulation in the new window. And then we repeat this process along the reaction coordinate value. And at the end of the day, what we have is several simulations which explore the full reaction coordinate phase space. Okay, so we are exploring the mechanism of our reaction. Okay, and then we can compute, for example, the free energy of the reaction, which is one thing we are going to do in the last step. Okay. Okay, so this is how umbrella sampling works. So let's come back to to the terminal. We were running, by the way, the QMN simulation. Let's see if it has finished. Okay, so it finished correctly. Here there is nothing special. This is the output file of our QMN molecular dynamic simulation, where again, let me go down 1 second. Okay, here. For example, again, we are printing the properties for different steps. For example, for the step number 15, we have, again, I don't know, the temperature, the total energy, kinetic energy, and so on. Now, the additional thing we have with respect to the classical simulation is the QN energy. This is the energy of the QN region computed at PM6 level, okay? But the rest is the same, okay? We also have here the trajectory that you can visualize together with the parameter file if you want, okay? Okay, so as I told you, in umbrella sampling, what we are going to do is to run a lot of independent molecular dynamic simulations. Of course, doing this manually is a lot of work. So what we are going to do is we are going to run the first window manually, let's say, in order to explain you the new things we need to have in the Amber input files. And then once you know what happened in one window, the only thing we need to do is to reproduce the simulation, just changing the value of the equilibrium distance of the bias potential, okay? And all the rest will be the same, okay? So let's then simulate manually the first window, and then we have one script in order to run sequentially all the other windows, okay? Okay, so we are here in the folder number 4, one window QMNMD. So what we need to copy from the previous simulation, from the QMNMD simulation, is the parameter files as usual, and the restart file, the last step of the simulation, which will be now the first step of the simulation, okay? Okay, so the run file, as usual, is the same as before. So again, we need to use Sander because we are running QMN. This will be the input file, the output file, parameters, the initial coordinates, which are the coordinates from the QMN simulation. Now, the final coordinates, I will call this file ini 4.30, okay? And the name, I chose this name because in our first window, when we run the full umbrella sampling simulation in the next step, I want the first window to have a separation between the two center of mass, so a value of the reaction coordinate of 4.3 angstrom, okay? This is why I chose this value. But you can change the name if you want, but it will be useful because later when we use the script to run all the windows in a sequential way, we need to modify this number in a systematic way, okay? Okay, so let's let's run the simulation while I explain you the new things in the input file. Okay. Okay, it's running good. So let's open the input file md.in. So this is very similar as before. So the first part is the classical part. So everything is the same. Remember, we restart the simulation from a previous file where we are reading coordinates, velocities, and box information, MPT ensemble. This is the barostat options, the cutoff, the shake approximation. Then we have the temperature and the thermostat, the number of steps, 200, because otherwise the simulation is too expensive, time step. Now we have the printing options. And now remember, we have now here two important keywords. The first one is about the QMN. Remember, we are running QMN, so we need this section, okay, that we have explained before. We have here our QN region, the electrostatic embedding, and so on. And now, this is also very important. That means we are applying special restraints. We have used already this keyword when in the heating of the classical simulation, right? But we can also use this keyword for other special restraints, and in particular for the umbrella sampling. Okay, so, and this is the umbrella sampling section. Here, okay, the three important things are the following. In this file, we are going to tell Amber how is our harmonic potential, our bias potential, okay? So here we are going to define the reaction coordinate, the force constant of the potential, and so on. Here we are going to print the value of the reaction coordinate along the simulation. Why? Because later in the last step, when we compute the free energy of the reaction, we are going to compute the free energy of the reaction from the probability distribution of the reaction coordinate. So we need the reaction coordinate value every n steps, okay, in order to compute the probability distribution. And here, this is the frequency with which we print the reaction coordinate. So here we are printing the reaction coordinate every step, okay? Usually here we print every 100 steps or 1000 steps in a real simulation, but since we are running only 200 steps, in order to have some data, I'm printing the reaction coordinate value every step, okay? Okay, so now we need to have a look at this file, distance.dat, okay? Okay, this file, I will explain you in a minute, is where we define the bias potential. But I will explain you later this file because I want to submit first the umbrella sampling simulation in a serial way because it will take few minutes. And then we can take these minutes in order to explain this file, okay? So, but I don't forget it, okay? So this is the file where we are going to define the reaction coordinate, okay? Okay, and here I already anticipate you. This is the value of the equilibrium value of the reaction coordinate. So here we are forcing the system to have a reaction coordinate value of 4.3. And remember, the reaction coordinate is the distance between this point here, which is the center of mass of these two carbons, and this point here. So 4.3 will be the initial value of our reaction coordinate, okay? Okay, so sorry. Okay, let's open the distance.out. So here, at the beginning of the simulation, the value of the reaction coordinate was not 4.3. It was almost 4.5. But then, as we are applying the bias potential, we are forcing the system to go to this value of 4.3, okay? And later you can see the reaction coordinate value is oscillating around 4.3, okay? Okay, and remember this file, ini4.3.rst, is the last step of this simulation, okay? The last step of the simulation. Now, we are going to take this step as the first step for the umbrella sampling simulation. So in theory, what we have to do is, let's say we have run the first window, right? Let's say this value is 4.3. So what we have to do now is change this equilibrium value to, for example, 4.2 or 4.1. So we need to decrease the value, okay? And then take the last step from this window as the first step for this window and run the simulation here. When this simulation finishes, we take the last step here as the first step of the next window and we run a new simulation, and so on and so forth. So we can do this manually, of course, but this will be too much work. So we can write a script in order to run this in an automatic way. Okay, later I come back to this file, I don't forget it. Okay, but for the moment, let's go to the step 5, where we have here this umbrella.sh, which is a bash shell script, where basically what we do is we create the input file for every window, and then we run the simulation in a serial way, in an automatic way. Okay, so if you like, you can explore in detail this script in order to understand exactly what we are doing. But it's indeed is very easy to understand. Okay. Okay, what do we need from the previous step? As usual, the DNA and the last step of the simulation, which will be the first step for the umbrella sampling simulation. Remember, I call it ini 4.30 because in this script, okay, 1 second, where it is, when we run Amber here, so here the name is of the initial coordinates is ini, and the value of the reaction coordinate, which at the very beginning is 4.3. Okay. Okay, so let's just execute the umbrella sampling script, and then this will take a few minutes. Okay, 1 second. I want to see. I think everything is fine, so it should run properly, but later I'm going to check. Okay, but in the meantime, let's come back then to the folder one window QMMD, and here remember we said before that in the input file of Amber, in the umbrella sampling section, which is this one at the very end of the file, we have here this input file distance.dat, which will define the bias potential. Okay. Okay, good. So let's understand a bit this file. So with this keyword, yet, here we will, let's say, describe the type of reaction coordinate we have. For example, let's say we write here 20 to 21. That means our reaction coordinate will be a distance between the atoms 20 and 21. If we have two numbers, the definition is a distance between these atoms. If we have, for example, three numbers, let's say 5, 6, and 7, the reaction coordinate is an angle, the angle formed by the atoms 5, 6, and 7. If we have four numbers, is the dihedral angle. What happens if we have -1? -1 means we are going to have a center of mass here and a second center of mass here. And the reaction coordinate is the separation between the centers of mass. So the first center of mass is computed as the center of mass of these two atoms. Okay, and the second one is computed as the center of mass of these two atoms. Okay, 140, 42, 172, 74. Okay, which are these atoms here. Okay, the 4 carbon atoms which will react. Okay. Okay. Good. So now we need to define our harmonic potential. And this is a bit weird in Amber because here we have 4 distances. Why 4 distances and 2 force constants? Why we have this? Okay, I have here a figure to explain it. So the umbrella sampling tool in Amber is thought to be able to represent this situation as bias potential. We have here a potential, then we have a flat region, and then we have again the other part of the harmonic potential. Okay, so with Amber you can define such a situation. For example, you can define a kind of wall potential in case you want to keep the system inside this region. Okay, how do you define it? So this potential is like the combination of two harmonic potentials. And you need to define the initial and the final distance which enclose the region where you are going to apply the bias potential, so R1 and R4. And also you need to define the equilibrium distance for the two harmonic potentials. Okay. So this is why we need 4 values in the input file, okay, in Amber. And also we need 2 force constants because we have 2 harmonic potentials. And of course, the force constant can be different for each potential, okay? What happens, as in our case, if we only want to apply, where it is, sorry, here. If we only want to apply a standard harmonic potential, well, so this is easy. What we have to do is to choose R2 to be equal to R3, right? Because if these two values are the same, then we have just one harmonic potential. And in order to have the same slope here than here, we choose the force constant K2 to be the same as the force constant K3. Okay, under these conditions, the same force constant and the same equilibrium value distances, we have a simple harmonic potential. Okay, and this is what we have in the input file, right? We have the same equilibrium values, 4.3, because we are in the first window. Okay, 4.3, and the same force constant. Okay. Okay, so that's it. Now for the second window, 1 second. Let me check that the simulation is running just in case. Okay, looks it's running well. So what we need? So in the next window, we need to decrease these distances, right? Because now the equilibrium value will be, for example, 4.2. Then in the next one, 4.1. In the next one, 4.0, until the reaction is complete. For example, when the distance is, I don't know, 1.5 probably. This is a carbon-carbon bond, right, which is formed. So the distance should be around 1.5. Okay. And this is what we are doing automatically here, okay, with this umbrella sampling .sh script. Okay. For example, okay, let me see in which point we are. Wait. Okay, so we have started in 4.3 and we are already in 2.2, so we are close to finish. But in the meantime, let's open, for example, the distance 3.8 that which is generated automatically by the umbrella.sh script. So here we have again the definition of our reaction coordinate. This is the same, right? Because the atoms which are reacting are the same. But now we have here the equilibrium value for the reaction coordinate of 3.8. And the potential, we are applying the potential in this range, okay, from 3.6 to 4, okay? If you open now, for example, I don't know, the 2.8, so we have the same, right? 2.8 as the equilibrium value, and then minus 0.2 plus 0.2, which is the range where we are applying the potential, okay? And the force constant is also always the same. Okay, so let's see where we are. Okay, 1.7. I think in 1.5 the simulation will finish, so we are already close. Okay, and now in the last step, as I said, we have a lecture in our YouTube channel explaining the umbrella sampling simulations and how to compute the free energy profile along the reaction coordinate. So in the last step, we are going to use a method which is called weighted histogram analysis in order to compute the free energy from umbrella sampling. Okay. So, okay, so it looked that everything has finished. Yes, perfect. So now, before computing the free energy profile, one last thing, which is nice. So here in each window, now, of course, we have this file, the mdcrd, which is the trajectory file. This is the trajectory file for each of the windows, right? If we want to visualize the reaction with VND, let's execute this script, movie.sh, movie.sh. This is a file which is using the CPP trash utility in Amber in order to select, let's say, the trajectories, and then we are going to put all together all the trajectories in this file md total, and then we can visualize this file with VND in order to see the reaction. Okay, let's do it. Sorry. Okay, I have to load Amber again because I opened a new terminal before and I didn't load Amber. 1 second. Okay, I load Amber with these two lines as before, and now I execute the script. It will take only a few seconds. Okay. So now we have created here this file. Okay. 1 second, because everything is fine, but just to be completely correct, we have only 30 windows, not 32. This is why the program complains here. Okay, but it doesn't matter. It creates the file anyway. So now this file is a trajectory file which includes the dynamics from all the windows, so we can visualize nicely the reaction. Okay, so we need to go to our graphical terminal, and before executing VMD, we need to go to the folder 5 umbrella QMNMD. Okay, so let's open VMD again, and we're going to see in a nice way the reaction. Okay, so file, new molecule. We need to load the DNA file, so I will write it here because I think it's easier. DNA dot parameter top load, and now we load the trajectory, the MD total, the one we have created now. Okay, remember to change here the type, Amber coordinates with periodic box load. Okay, good. Okay, it's loading. I will again translate the system to see it, and now I will just represent the DNA strand. Okay, 1 second. So one thing, since during the simulation, as you can see, the DNA strand is moving a bit, it translates. So you can remove the translation of the system, because then it's easier to visualize. Going to extension, analysis, RMSD calculator. No, sorry. No, it's not here. Extensions, analysis, RMSD trajectory tool. And here we write nucleic, and we're clicking align, because in this way we remove the translation of our system. Okay, so now we are only representing the vibrational motion, which is the relevant one. Okay. Okay, so I'm going to represent here in graphics representation. I will create a new representation with the atoms of the QM region, okay, which are, remember, let me check, 3952, 39 to 52, and 1 second, 7184, 7184. Okay, and I'm going to choose the licorice representation. Okay, so let me rotate this in an appropriate manner. Okay. Here it is. I'm going to also delete the axis, display axis off. Okay. Okay, so also I'm going to remove the perspective. So I'm going to choose the orthographic representation, which I like more, but this is just a question of taste. Okay, so here we are at the beginning of the simulation, right? In the step 0. So the reaction didn't start yet. Now I will go slow down a bit this. We click play, and then you will see the two thymines will react with each other, right? So they are approaching. Okay, let's accelerate it. Okay, so here we are. Here we have the reaction complete, right? Of course, the bonds are not printed because it is a question of representation. I think we can change this. We can, let me see. We can choose here bonds, I guess. Yes. In the drawing method, you can choose bonds. No, this is, sorry, dynamic bonds. And here we can choose the distance cutoff. I will choose, I don't know, 1.8, for example. That means BND will print a bond here if the distance is smaller than 1.8, okay? So, and then if you want, you can, again, visualize it. And now you can see the bonds if you prefer the bond representation. Okay, so here we have our reaction. Okay, so that's a nice reaction. So the simulation finished correctly. And the last thing we need to do, if you want, is to compute the free energy profile along the reaction. Okay. So the last step, let's go to the folder 6.1. Remember, 1 stands because we are going to use the weighted histogram analysis method in order to compute the free energy from the probability distribution of the reaction coordinate. As I said before, you can go to our lecture in the YouTube channel to see the equations and how this works. Okay. Here we are going to use it as a black box because the exercise was already long enough. And what we need here is this input file, meta.dat. And in this input file, we tell the program where the distance.out file is located for each of the windows. Okay, remember that in this file, we have the value of the reaction coordinate along the dynamics. Okay, so from here, we can compute the probability distribution for each of the windows and then the free energy in each of the windows. We also need to provide the desired reaction coordinate value, okay, which is, remember, from 4.3 until until 1.4, okay. And finally, we need also the force constant. If you remember, the force constant we use in our simulation, okay, 1 second, is 500, okay. And now we are writing here 1000. This is because the WHAM program used the definition of the harmonic potential as 1/2 multiplied by the force constant and so on. And Amber doesn't use the 1/2. Okay, so this is why this number here in the WHAM input file has to be the double than the force constant employed in Amber because of this 1/2 term. Okay. Okay, so let's execute WHAM. In order to execute it, we need to provide the initial value of the reaction coordinate, 1.4, the final one, 4.3, the number of beams we want in our histogram. So that means the number of points, we want to compute the free energy along the reaction, okay? This is the tolerance for the WHAM equations. If you go to our talk about umbrella sampling, you will understand better why we need a tolerance, because the WHAM equations has to be solved in an iterative way, okay? This is the temperature, 300 Kelvin. This number means our reaction coordinate is not periodic, the input file and the output file. Okay. Okay, everything finished correctly, and this is the output file. Here, the important thing is we have here an infinite, so it doesn't matter. When you have here an infinite, is because we don't have we don't have populated this reaction coordinate value during the simulation. So if you like, we can delete this line. Okay, doesn't matter. Okay, so we have here the reaction coordinate value and the free energy for this reaction coordinate. And here we have this weird thing, because we can also do some statistical analysis that we didn't do. This is why it prints none and 0 and so on. Okay, but it doesn't matter. Okay, you can forget the last 3 columns. The important thing is the reaction coordinate value and the free energy. Okay, so we can represent the free energy profile if you want with GNU plot. So we need to go to our other terminal, and we move to the folder 6.1. And now we need to load GNU plot in this way. So, wait, sorry. Okay, so module load auto load GNU plot. Okay, so let's call GNU plot. And now we can plot the file pmf.out using the columns 1 and 2 with lines, for example. This is enough. What's the problem here? 1 second. Okay, because we have this infinite number still. Okay, let's delete it. Okay, sorry. Okay, let's try again. Okay, so, okay. 1 second. What's the problem? Maybe we have another infinite value, or 1 second. No. PMF. Okay, I wrote PFM. Okay. Okay, so let's try again. Is PMF. Okay. Okay, now here it is. Okay, so this is the free energy profile. Remember, the reactants are on the right side, the products are on the left, because this is the separation between the carbon-carbon center of mass. So here, as you can see, the reaction barrier is crazily high, is 95 kilocalories per mole, and the reaction energy, the reaction free energy, is around 70 kilocalories per mole. Of course, I told you when we started the exercise, the barrier in the ground state is very large, but it's not as large as the value we obtain. We obtain this crazily high value because we are running very short simulations, okay? Each umbrella sampling window ran for only 200 steps, okay? Which is 400 femtoseconds, which is nothing, okay? In order to have a realistic profile, maybe we have to run 20, 30, 40 nanoseconds per window, okay? And then we're going to obtain something more realistic, maybe an energy barrier of 15 or 20 kilocalories per mole. If you want, you can try to run the simulation not with 200 steps per window, but maybe with 2,000. And I mean, you have to wait maybe 1 or 2 hours, but it is okay. And then you can recompute the free energy profile, and you will see that the barrier and the reaction energy decrease already maybe 10 or 20 kilocalories per mole. Okay. But the important thing here is we are able to compute the free energy of the reaction, and for this we have combined QMN with molecular dynamics with umbrella sampling. Okay, so this combination, the combination of QMN with molecular dynamics with an enhanced sampling technique, maybe not only umbrella sampling, but metadynamics or I don't know, accelerate dynamics or replica exchange or whatever method is very useful. Okay, it's very powerful. Okay, so that's it. So I'm going to close this. So this was the computer exercise. So we have simulated the thymine-thymine dimerization, and now I will tell you probably in the coming days. Part of this computer exercise will be the homework for some of you. Okay, this is why I did this video, because I know we have employed a lot of techniques, and otherwise it will be very difficult for you to run. So, but I think with this video you will be able to run this thymine-thymine dimerization simulation, and yeah, and that's it. If you have any question, you can also contact me by email. Okay, so good luck with the homework, and yeah, see you soon. Bye.